Hello. So this is Hadi. He's helping me with some things, and this is where I work. In here.
Hello, how are you?
Hi, nice to see you.
This is my computer, and then a whiteboard that has like equations on it that I sometimes look at. Those are the ones that I'm looking at up there. The first one is the Kelvin equation, and the second one is classical nucleation theory. Will you turn around? Sorry. And they're right there. And I sort of explained this over lunch, but I'm looking at nucleation, which is when it sometimes occurs during a phase change, when the new phase appears in little clusters. And I'm specifically sort of focusing on this from the angle of it. That's a process that happens a lot in the atmosphere that has a pretty big effect on climate change. And we don't know very much about it because both of these models don't exactly come up with the accurate results that conform to data from experiments and simulations. So I'm going to be looking at those. I've already compared those two specifically against each other, and they don't describe the same thing. They're not identical. And I've written a program which will get results from this, which I will compare to results from simulations done by the lab previously. And then I'm going to be looking at other factors that might influence nucleation, and I'm going to see if I can make these reflect those factors and hopefully be more accurate. And that's, yeah. Any questions? Yeah.
Can't you explain the top equation?
The, which one?
P is equal to P naught.
Okay.
No, she doesn't care
So
to.
that's vapor pressure, and I think that's saturated vapor pressure. And then that's E to the, and then C over R, I think that's surface area, that's what that is. And then this is free energy, and free energy at equilibrium equals 0, so I'm mostly focusing on when it equals 0. And that's the pi, and that's the radius of the cluster. That's a drawing of a cluster, I guess. Surface tension, and then chemical potential. I'm looking at, there are several versions of that that are identical, that have the number of droplets instead of the radius. So you can convert in between those two, which is a little bit easier.
Excellent. Anything else you want to show us?
I don't think so.
Okay. Do you want to say just
Yeah.
a few words?
How high above sea level are
Guys,
you
why
looking?
don't we come out here?
I'm not really looking at specifically in the atmosphere, like this will apply to all of them, but I think they exist throughout the atmosphere, the aerosols. And I looked it up, and I think mine, the clusters can be from like 10
Over here.
nanometers to 100 microns in what I've looked at, so it'd be in that range, so I wonder if they are the same way.
How big is a micron?
It's a micrometer.
Very small.
Yeah.
It's less than a meter.
No, 1 micron is equal to 1 micrometer.
So 1 million millimeter. So just
10 to the negative 6.
It's easier to say micron than
So
micrometer.
Clara, and
Yeah, so our research group focus on the simulation, and we use some small system size to represent the real system, and we usually put our molecules in a simulation box. We have, for example, 100 or 1,000 molecules, but then we use some tricks to make these simulations, to make the system similar to the real system, to the bulk system. So the idea is that we have this simulation box, and then it can have interaction with the images of the simulation box, and we use a concept which we call minimum image convention, where whenever we have a molecule in this simulation, so if, for example, this is one molecule here and this is one molecule here, so instead of calculating the interaction with this molecule here, we use the image of this molecule here to calculate the potential energy. And there are some fundamentals, there are some basic things that we need to run the simulations. one is the potential energy surface for our simulations. Like we should know how the molecules interact with each other, and for that to be possible, we can have empirical force fields, or we can use initial. So this one is just obtained by some feeding. So we have some experimental data, and then we simply fit our properties, and we obtain some parameters for the potential energy. This one, though, is obtained by some rigorous theories. I don't know if you have heard of like quantum mechanics. So we do use some quantum mechanical calculation to obtain the potential energy here, and we eventually want to solve the problem with these potential energy surface. The other one is, I can say, it's a little bit technical, but I try to be